So point groups. What are point groups? Well, once we find out the symmetry elements in a given molecule, then we can group those molecules together when they share particular types of symmetry elements, and we call those groups point groups. For example, this is a C1 point group, and the only symmetry operation of this point group is the identity operator. There are no other symmetry elements on the C1 point group. You have a sigma infinite V point group, and that means that they have a C infinite axis of rotation. This is typical of linear molecules. You can have, if you think of the axis going through, let's say this is, for example, could be hydrogen fluoride or any carbon monoxide, or the anion of the cyanide anion. And if you imagine the asymmetry axis going through that bond between the two atoms, you can have an infinite rotation around that axis. That's what it's called, C infinite, and they all give you the same configuration. And besides that, they have an infinite number of sigma V planes. They contain that rotation axis, and again you can have infinite planes around that rotation axis, sigma V's, and they all give you an identical configuration. And they do not have a sigma H, so no plane that is perpendicular to the principal axis, and no inversion center. So asymmetrical diatomic molecules, hydrogen fluoride, hydrogen chloride, hydrogen bromide, and carbon monoxide, meet that criteria. And also a polyatomic molecule which is linear, that does not have a center of symmetry. And for example, I give here the example of hydrogen cyanide. So these molecules, the three atoms, sit in the same axis. There's a C infinite. They have sigma V planes, but they do not have any inversion center. They don't have any, and they don't have any sigma H. No plane that is perpendicular to that C infinite, that principal axis. This sigma H, this is typical of the atomic molecules which are symmetrical, or linear polyatomic molecules that have a center of symmetry. And a typical example, not the only one, is for example the molecule of CO2, or the molecule of acetylene. And as symmetrical diatomic molecules, H2, O2, N2, etc., Cl2, they have a C infinite, because they are linear molecules, so you have infinite rotations around that axis, and they will all give you identical forms of that molecule. But they have a sigma H, a plane perpendicular to that sigma C infinite, and again an infinite number of sigma V planes. An infinite number of planes that contain that C infinite, and one sigma H, one mirror plane which is perpendicular to that C infinite. TD, OH, and IH point groups. These are highly symmetrical molecules. They are point groups that possess many symmetry elements. The typical example of a tetrahedral molecule that belongs to a TD point group is, for example, the molecule of methane. And an example of an octahedral molecule is what we looked at before, the xenon hexafluoride. And that had many inversion centers and quite a few axes of symmetry and reflections and mirror planes, etc. So they are highly symmetrical molecules. So how do you determine the point group of a molecule or a particular molecular ion? How do you determine to which point group they correspond? Well, you look at the symmetry elements and then see in which category, in which particular point group they would fit. And to do that, we use something called character tables, which are decision trees that help you identify what your molecule, to which point group your molecule belongs to. This is just an example. They are all very well. They are all the same. They just have a slightly different look, but they are all based on the same symmetry and questions. So you start here and you start interrogating your molecule, looking at the symmetry elements it might have until you end up in a particular point group. So let's try this decision tree, this character table, with the trans N2F2 molecule. Stop the video now, have a look at this molecule, and try to identify to which point group it would correspond by using this decision tree. So please stop the video now. I hope you stop the video and have a go and try to identify the point group for this molecule. And believe me, the only way of learning to do this, to use character tables, is by practicing and using them to identify many molecules until you get used to use them. So let's start. Is the molecule linear? Well, it definitely is not linear, so that's a no. Does the molecule have a TD, OH, or IH symmetry? Remember tetrahedral, octahedral, or icosahedral symmetry? Well, clearly no, it's not. It doesn't look like a tetrahedron, an octahedron, or an icosahedron. Is there a CN axis? Yes, there is. There is a C2 axis that goes in between the two nitrogen atoms and is perpendicular to the plane where the molecule sits. So if you imagine as an axis going through those two nitrogens, the bond between those two nitrogens, and perpendicular to where the plane in which the molecule sits, a rotation of 180 degrees would swap the fluorines around, and you will have an indistinguishable configuration of this molecule. So yes, there is a C2 axis. Are there two C2 axes perpendicular to the principal axis? So if our principal axis go through the molecule is perpendicular to the plane where the molecule sits, what the question is asking is, so in the plane where the molecule sits, perpendicular to that C2 axis, are there other two C2 axes? And no, the answer is no. If you imagine in the plane of the molecule an axis going this way or this way, a rotation of 180 degrees will not give you an identical configuration of that molecule. So that's a no. Does it have a sigma H plane? Does it have a mirror plane perpendicular to the principal axis? Well, yes, it's the plane in which the molecule is sitting because it's a planar molecule. So we have a yes, and then we reach to a stop. And if we go to the character table, it will conclude that the point group for that molecule is C2H. So what about the molecule of phosphorus pentafluoride? What would be the point group for this molecule? So again, I'm going to ask you to stop the video and have a go at identifying the point group for PF5 using this character table. Stop the video now. So let's make a start. Is the molecule linear? Well, no, it definitely is not linear. Does it have tetrahedral, octahedral, or icosahedral symmetry? Well, no, it doesn't look like a tetrahedron, an octahedron, or an icosahedron. Does it have any CN axis? Yes, it has. It has a C3 axis that goes through this fluorine, phosphorus fluorine bond contains a sort of the phosphorus and the two axial fluorine atoms. Are there C2 axes perpendicular to the principal axis? Yes, There are three of them, and they go through each of these fluorine phosphorus bonds that are in the equatorial position. So that's 180-degree rotation around that bond with those two fluorine around. So, and you have one of each, one C2, going through each of those phosphorus fluorine equatorial bonds. Is there a symmetry plane, sigma h, that is perpendicular to the principal axis? Yes, the one that goes contains the phosphorus and the three equatorial fluorines. That's a mirror plane, and it's perpendicular to the C3. So we have reached the end of the character table for PF5, and the point group is T3H. The following slides are just an example of molecules that belong to each of the point groups that I've mentioned in the character table, and that you can use to practice to see if you can identify those molecules as belonging to those point groups. And there is no other way of learning how to use a character table but practicing until you get your head around what symmetry operations, what symmetry, access, mirror place, etc. you are looking for. So I would encourage you to try all these molecules and see if you can identify the different point groups. Another table with common point groups and their symmetry elements, and some examples of molecules that belong to those particular point groups. So again, a good way of practicing using character table to see if you can identify those molecules as belonging to those point groups.